we spent the entire class so far basically talking about limits, right? That's what we've been up to. And I know it seems maybe it's kind of silly, but we're going to finish this section by formally defining what a limit is. And I know that kind of feels like, well, didn't we already do that? And haven't we been using the definition of a limit this whole time? And the answer is yes, we've been using the definition of a limit, but what I'd like to do here specifically is talk about the very careful mathematical definition of what a limit is. And so this, definitions that look like this, that have Greek letters in them like epsilon and delta, so these things I'm highlighting right now, these are very, very common expressions in higher math. And what I'm about to show you is going to be a little confusing. I understand it is. I remember the first time I saw something like this, I was like very, very confused. And I really didn't start to get a handle on this kind of stuff till graduate school, to be perfectly honest with you. And so just know that this is going to be a little bit tricky, what we're going to look at. And know that this is not something that I test on. Okay, you'll never see something like this in a homework or on a test, but I'm going to present it to you in hopes that it shows you what advanced math courses look like. And if you're thinking about being a math major or the stuff interests you, you might consider taking some advanced courses. That's sort of the goal of what I'm about to show you. Some pretty abstract math. Okay, so let's look at the formal definition. So it says let's let I be an, and let me just clarify too. I'm going to try to relate this definition to the pictures down here to explain carefully what it says. Okay, so let I be some open interval around the letter C. In the picture down here, I is the interval on the x-axis, right? This is I. It's what's between the 2 points we care about, and C in this particular example is 4. So this limit as x approaches C equals L. What that means is that no matter what number we pick, so for any epsilon bigger than 0, there's some delta bigger than 0, such that if x minus C is less than delta, inside absolute value, then f of x minus L is less than epsilon. So in English, so not math terms, what this says is the limit exists if, no matter how close you want to be on the y-axis, you can pick some interval on the x-axis such that if you're within delta on the x-axis, you're within epsilon on the y-axis. And so just to kind of clarify a little bit further, this down here is the x-axis we're talking about, and this right here is the y-axis. Okay, so I'm going to draw some pictures on the graph down below to kind of illustrate what I'm talking about here. And let me also set it up top here. So the idea is you choose some distance delta so that if x, this is what I said in English, I'm just writing it down just so you can have it. So if x is within delta of C, the function output, I should say, is within epsilon of the limit L. So these are the kind of like abstract general statements we make in math to say what a limit is. And let me take you into a specific example to kind of illustrate what it says. And epsilons and deltas are the common letters that are usually used. Okay. Can I clarify something about that? I mean, there's not a whole lot to clarify. It's probably confusing so far, but is there anything that people want to say so far? So let's use this concept to show that the limit of the square root of x as x approaches 4 is 2. And that's what's being plotted down at the bottom here. This is a graph of square root of x, and it's a visual representation of this limit, right? So first of all, we know that this is true, right? As x approaches 4, the square root approaches 2, and we know that's true because when we take the square root of 4, we get 2, right? So square root is actually a continuous function, and so we can just plug the number right in there, and we know that the answer is 2. But let's look at it carefully in terms of this careful mathematic definition. Okay, let's pick an epsilon. And in this particular picture, you can see that epsilon is being chosen as 1/2. And so we're going to go with that and work with that. So let's let epsilon be 1/2. So suppose epsilon is 1/2, 0.5. The question is, how close to x equals 4 do we need to be? Oops, only one E. In order for the square root of x to be within 0.5 of the value of 2. And I actually have a little applet here set up to show you what this looks like visually. And again, this is one of the more conceptually challenging things that I recall learning as a math student. And so the more pictures we could show to explain this, the better. I'm gonna let people finish writing this down before I share my screen and show this applet. And again, that's kind of what's being shown on the visual here, right? Epsilon is 0.5. Well, I'll come back to that in a second, actually. Let me let you finish writing that. All right, just kind of looking here. Looks like most people finished writing. I'm going to share my screen. Of course, I can't see everyone, but I'm going to go ahead and assume everyone's all set. Let me share my screen and show you this applet of the situation. Is this working? Doesn't really seem to be working. Okay. So here's the situation, right? This is the square root of x. This is just a graph of the square root. And we are looking at the limit as we're approaching 4, right? So c in this case is 4. Notice how when I put a 4 in here and I hit enter, it puts a bracket around the thing we care about, right? And then the limit we know, because the square root of 4 is 2, and so that's going to be 2. And notice when I put 2 in there and I hit enter, it puts a bracket around the y values, right? So the c are the x values, as I mentioned. L are the y values. It's the output. And you can see there's sliders up in the upper left-hand corner here for epsilon and delta. And so the idea is, and notice how when I slide epsilon, let me go ahead and slide it a little bit. Uh-oh, come on, internet. When I slide epsilon, it makes that thing bigger or smaller, it makes the space bigger or smaller, right? And when I slide delta, it makes the other one bigger or smaller. So let me make this one really small just so it kind of gets out of the way. The question is, let's say we want to be within, in this case, it only goes up to 0.4. So let's say we want to be within 0.4 of the limit, right? So I made epsilon 0.4, and it's now made a bound around the y values between 0.4 less than the limit and 0.4 above the limit, right? So if you look over here on the y-axis where I'm kind of showing you with my cursor, this lower point is 1.6, right? Because it's 2.4 minus 0.4. And this higher point is 2.4, because we're creating a buffer of 0.4 around the limit, right? So if we want to be within this close in the y value, I'm going to extend the delta now until it matches up with the endpoints. And this is too big, actually. I need to make this slider bigger. Can I make this slider bigger? Can't make it bigger. So let's make this one smaller. Let's say we want to be within 0.1 instead. Let's make it 0.2. Can I get that close? No, I can't. I got to get even smaller. Let's say we want to be within that close. Right, so the biggest point that it hits right here on the graph is right here, where I'm kind of showing you with the cursor. And the smallest point is right here. And so I'm going to make delta bigger until it hits those two values. Right, so I'm hitting it until it hits those two edge values. And it looks like I have to extend it all the way to 0.4 to make that happen. And so what we just learned is I need to be within 0.4 of 4, right, of x equals 4, in order for the output to be within 0.1 of the limit. And if I want to get even closer, right, if I want to make epsilon even smaller, then that means delta needs to get even smaller as well, right? If I want to get closer, then this needs to get closer. And so every time epsilon gets closer, delta needs to get closer. It's basically saying, how close do I need to be around the x-axis in order to make us this close around the y-axis? And so I'm going to switch back to my iPad in a second and show you that on the graph. Does anyone want to say anything about this picture? I'm going to draw the same, basically the same thing on the graph in a second. Let me go ahead and stop sharing and do the same thing on my iPad here. So back to our image. There we go. If we want to be within 0.5 of the output, the question is, how close do we need to be on the input? Oh, give me 1 second. I just accidentally closed this out. Oh, I closed that one out too. That wasn't a good idea. Right? Yeah. Okay. So what we want to do is we want to be within 0.5 of the limit, right? So over here on the y-axis, is this following? Yes. This is the epsilon part, right? This is taking the limit above and below the output, right? And so the question is, if we want to be within this range, and let me go ahead and highlight it with red, right? If I want to be somewhere within that piece of the graph, right? If I'm somewhere on that red line I just highlighted, I'm within 0.5 of the output of 2. The question is, where do I need to be on the x-axis, right? Well, very clearly, just looking at the picture, I need to be between this location, right, and this location. And so if delta is somewhere in here, then the output is going to be somewhere within that range. That's sort of what we're trying to say. But let's say it mathematically. Let's say it carefully mathematically. Right? And I'm going to draw a line down the middle of the screen here because we're going to split this up into two different things here. Okay. So let's pick our epsilon to be 0.5. If we want the output to be between 1.5 and 2.5, the question is, what does the x value need to be on? Well, that means the square root of x needs to be between those two numbers. Right, so we just kind of, from here to here, we know that, let me do that in another color. From here to here, we know that y equals square root of x, so I just substituted in square root of x. So we want the y values to be between 1.5 and 2.5. Well, the y values are achieved by square rooting x. Okay, so now we want to just figure this out. So let's square both sides. So from here to here, we're going to square all the terms because we're trying to get a condition on x, right? And so if I square everything in that expression, it becomes 2.25 is less than x, which is less than 6.25. So I just squared everything to get rid of the square root. And what this says is, as long as x is between 6.25 and 2.25, our output is going to be between 1.5 and 2.5, which is what we were trying to figure out. Okay. And so let me just figure out what delta is then, right? So I want to be between those two numbers. So let me go ahead and label that actually, right? This right here, what we just figured out, this is 6.25. And this point right there is 2.25. But what does delta need to be? Because we want to create like an even interval on either side of 4. And that's not an even interval, right? It goes up by 2.25 in one direction, but only goes down by 1.75. In other words, what I just figured out, just kind of looking at that picture and thinking about this, 4 minus 2.25 is 1.75, right? That's going to the left. 6.25 minus 4 is 2.25. And so if we want to make sure we're inside that correct range, we want to choose the smaller number. And so based on those two things, 1.75 is smaller. And so that's going to be our delta value. In other words, what all this has just, what we just figured out based on all this information is that if x is within 1.75 of x equals 4, then the output, in other words, when you square root it, that's what you get when the output happens, right? Then the output will be within 0.5 of the limit. Kind of relating it back to the definition at the top there. That's what we would say in words. If we wanted to say that mathematically, i.e., what we would say is if x minus 4 is less than 1.75, right? That's our delta value. Then the square root of x minus 2 is going to be less than 0.5. That's our epsilon.
It cuts off slightly. I can't read the bottom there.
What are you using? Using a computer? Just curious. You on a computer, Gregor?
Yeah.
What's the last thing you see? Because I see it on my screen. Just trying. It'd be helpful to know where it cuts off.
I see IE, and then the rest of it just cuts off.
Okay.
So that's good right there.
Yeah, by all means, let me know if that happens. I'm keeping an eye on my own screen, and I can see it on my screen. I'll always be sure that I can see it, but obviously I'm not able to see what everyone sees. I think there's some weird thing that happens between computers. Anyway, formatting. Can I ask you some questions about this? We're going to do this in general in a second. So we're going to actually make this more careful and more general than it already is. I've picked specific epsilons, right? I'm saying I want to be within 1/2 of that limit, and what I just determined is if I want to be within 1/2 on the y values, then on the x values I need to be within 1.75 of 4. Which is, maybe that's interesting or whatever, but what we want to do is we want to say how close we need to be no matter what epsilon we choose. And so that's what's going to go in this sort of blank space that's currently open, is an even more generalized version of what we just did. And again, this isn't something I'm going to test you on. I'm hoping that math majors or people who are interested in thinking about things abstractly might be interested in this, and it might encourage you to take some more math courses or come talk about it or whatever. Just giving you an idea. Like if this was a course where it was only math majors in it, we'd be digging into this kind of thing pretty deeply. But since this is a course it's a general education course that covers lots of different majors, we usually kind of skip over this in our school at least. Anyway, questions before I sort of mention this in general now? All right, let's make it super general. So again, I chose on this left one, I didn't choose, I took it from the textbook, but the textbook chose epsilon to be 1/2, right? So it sort of set an interval around the limit. Let's make an arbitrarily small interval. So let's let epsilon be some really small number. So let's epsilon be positive, but think about it as a really, really small number. So we want to get really, really tight. We want to get infinitely tight around that limit is the way to think about that, but still some interval. And so in general, what we want to do, we know the limit is going to be 2, right? And so we want the difference between the output and 2 to be as small as we want. Right, so when you say let epsilon be bigger than 0, and you say it could be anything, and then you write down y minus 2 less than epsilon, that's saying we want to be really, really close to 2. All right, let's do the exact same thing we just did a second ago. So this absolute value expression that we just wrote down, if you remember back to pre-calc, that changes into this expression. I'm not going to go into detail about that. Hopefully you remember that. That's just the definition of absolute value. Well, we know that y equals the square root of x, and so we can just substitute in square root of x. Let me add a couple of these things. So here to here, it's the definition of absolute value. From here to here, we just let y equal square root of x. Let's keep going. We're trying to do the same thing, but instead of having numbers in here, I'm just going to leave epsilons and deltas, right? So let's get x by itself in the middle there. So I'm going to add 2 and then square both sides. Or square all sides, I guess I should say. Right, so just added 2, so everything gets a plus 2. And then when you square it, it gets rid of the square root. And so this is the sort of the analogous stage as we were a second ago right here, right? Those two things I'm connecting with the red line. We're sort of saying, as long as x is between these two values, then the output is going to be less than epsilon, except on the left, what we did first, that's specific numbers. On the right, it's in terms of epsilon. So when you pick an epsilon, it tells you how close you need to be. You see that? So pick an epsilon right here and right here, plug it in, add 2, square, and that would tell you the interval around x that you need to be in order to be that close, right? So let me keep writing this down. Let's keep going. So let's square this out. We'll square out the epsilons, and let's get even more specific. So when I square that out, I get 4 minus 4 epsilon plus 4 is less than x, which is less than a very similar expression. Now let's factor, right? This is almost the same thing. We've got 4 plus or minus something. And let's factor out a -1. And so this is the same thing that looks like this. Yeah. No, that's not what I wanted. I messed this up a little bit. This should be an epsilon squared. Sorry, I can't read my own handwriting. And so then this becomes epsilon squared. Yeah. Right. So all I did is just factor out a -1 because I wanted it to say 4 plus something and 4 minus something. So it's telling us, it's saying like, if you want to be at 4, you need to be a little bit to the left. This is telling you the left part, right? And then a little bit to the right. This is telling you the right part. And again, it's in general. We don't even know what epsilon is, but you pick an epsilon and then it'll fall out. In other words, let me sort of write a sort of takeaway thing. Since epsilon is any positive number, 4 epsilon minus epsilon squared is actually less than 4 epsilon plus epsilon squared, right? In other words, when you subtract a positive number, it's less than adding a positive number. And so that's the smaller one, and so that's our delta then. And so that means delta has to be less than that expression. If that happens, then we will be within epsilon of the limit. This is sort of this is the takeaway, so I'm going to box it in a little bit. And so notice how epsilon's any positive number. So on the left, it could be 0.5, right? So we let it be 0.5 here, but it could be any positive number. It could be 0.1, it could be 0.01, it could be 0.001. And so as epsilon goes to 0, right, the delta value goes to 0, and we get closer and closer and closer to the number 4. Right? So this is a generalized way to write down it's what's called the epsilon delta proof of the limit. That's how people often refer to this kind of thing in math. I would love to talk about this a little more if people have some questions or comments about it. And again, I know it's not the most easy thing to understand, and after this page, I probably won't ever return to this. But if this is the kind of thing that's like, oh, that's kind of cool, I see how you're generalizing that, and I'd like to learn more about it, then that's why I'm doing it. I hope you take some more math classes. That's sort of the thing you should think about. Or I could help direct you if you wanted to think about that. Can someone say something about this? Ask a question about it. Love to hear general thoughts.
It actually does kind of like break down like the idea of a limit more easier.
I've never heard that, but that's really nice to hear. Thank you. Yeah, sometimes I worry that this confuses people. So sometimes it helps hearing like, oh, that actually makes sense. And if it does confuse you a little bit, that's okay. Look, because it's a confusing thing, to be perfectly honest. And just know that this is we're just breaking this down into more and more abstract ways to think about it, which is what we end up doing in math. We think about things extremely abstractly. And this thing I boxed in at red at the bottom here, right? This thing right here is as abstract as it gets, right? You pick how close you want to be on the y-axis, you pick an epsilon, and it'll tell you how close you need to be on the x-axis to get that close. Even if there's a hole there. I want to remind you about that too, right? This example we looked at is the square root, and it doesn't have any holes or discontinuities or any weird stuff. So that's an easy one, right? What I've just shown you, though, works with complicated, weird functions too, is kind of the powerful thing about that. Thanks for that comment. Other questions or comments?
Also something to add on. I don't understand like why there's a smaller side and a larger side of epsilon.
Yeah, so the idea is like, if I just zoom in on this picture a little bit, if we want to be between here and here on the y-axis, because this line, it kind of looks straight, but it's not straight, right? It's curved. It's square root of x kind of has like a curved shape to it. And so if we want to be between those two lines I just drew in red, then we want to be between these two places on the x-axis, right? But that's not an even interval around 4, right? Like, in other words, this distance right here, and that I just did in green, is less than that distance. One of them is like 1 point, and you can, oh, it actually says right there, right? One's 1.75, one's 2.25. And so we want to pick a specific interval that's even around 4. And so if we want an even interval, we want to make sure we pick the smaller number, because that'll make sure we stick inside the blue lines I just drew, right? In other words, if delta was 2.25 instead here, that's okay on this end because it would align there, but over here it would be over outside, and then we'd be outside the region up there. Does that make sense?
Yep.
So we picked the smaller one just to make sure that the interval is inside of what we're trying to achieve, right? We want to be somewhere between there and there. And so that means we want delta to be the smaller one. And so I guess then that means this doesn't happen, right? It doesn't hit there. It actually hits a little bit before there. It'll hit at 5.75. And we'll actually be up here, which is fine because we're still inside that zone. Yeah, that was a good thought there. That shows that you're definitely following along with this argument, I'd say. And that was just for the specific example, right? For the general example, it was a little bit more tricky. We have the same kind of thing where we were looking at like 4 plus or minus something. Let me zoom out a little bit so you can see it all. Right, that's 4 plus something, 4 minus something. And I was trying to figure out like, which is the bigger one? And it turns out, since epsilon's positive, that when you take something and add a positive number, that's going to be bigger than taking something and subtracting a positive number. And so that's how we figured out which the bigger one was. And that's why we used the smaller one. Yeah.